Lesson 8.2, Solving Trig Equations. Now that we have gone over 2 days of simplifying and verifying trig identities, we are now going to use that knowledge and our prior knowledge of reading unit circles to solve trig equations. So reading here in this beginning sentences, solving trig functions, or more accurately, solving trigonometric equations, is the process of finding the value of an unknown angle, usually denoted as x or theta. I'm not sure why those are showing up that way, which makes the equation true. Unlike linear equations, x plus 2 equals 5, trig equations are periodic, meaning they repeat their values at regular intervals. Therefore, solving them usually involves finding multiple solutions or a general formula for all possible solutions. What you guys are going to realize though is I am only going to require you to find solutions in one um, 360 degree uh, domain constraint. Okay? So in solving trig functions, you will notice that there are some steps we will take. Our goal is to isolate the trig term using algebra. We are going to use all our identity formulas to help simplify wherever necessary. That's what you did in the prior section in 8.1, day 1 and day 2. And we're going to find that reference angle using that unit circle and apply periodicity if general solution is required. Step 5 is not going to be required with you guys. Okay, so let's go ahead and tackle example number 1. Well, you know what? Before we jump into that, let's look at this for a second. So here's our unit circle. Reminder, our sine, our cosine, and our tangent are assigned a y, a x, and tangent is always going to be the y coordinate over the x. So again, x coordinates, y coordinates, and anytime we are dividing y over x, especially in the three angles that are within the quadrants, these which I'm showing you right here, don't forget when you're dividing y over x or x over y, we will go ahead and we ignore the 2's because when you divide a half divided by square root of 3 over 2, the 2's cancel. So in all these situations here, when we are evaluating tangent or cotangent, you can just go ahead and ignore those denominators. 1 over, say reciprocal, and of course, this is just the reciprocal. So again, that is all that we were doing before in the previous unit, so it's just going to be a repetition. So starting off real simple, our goal is to isolate cotangent. So the first thing we're going to do is add 1 to both sides because our goal is to isolate cotangent. So we have a square root of 3 cotangent of theta is equal to 1. Then I'm going to divide both sides by square root of 3 in order to get rid of that coefficient. And now cotangent of theta is 1 over square root of 3. So our goal now is to find theta. So in essence, theta is going to be the cotangent inverse of 1 over square root of 3. All right. And that just means that we're going to go look for that angle that satisfies this. Now, cotangent, we know, is x over y. All right. So I'm just going to look to figure out how this ratio here, x over y, can help me find my answer on the unit circle. So my quantity is a positive quantity, all right? So I know that my final answer needs to be positive. And if you recall, when it comes with, when we're looking for angles that deal with cotangent or tangent, once you find one of the angles, you can use the slide rule to find the other one. And if you don't know what I'm talking about, I'll show you in a second. So 1 over square root of 3. So since it has to be a positive value when we divide, for sure we know our first angle has to be in this quadrant. And our x was a 1 and our y was a square root of 3. And the only one that where we have an x as a 1 in the numerator and a y as a square root of 3 is angle pi over 3 or 60. Okay, so x over y, again, let me show you here. It was x over y ends up being 1 over square root of 3. And just to give you the visual as to why we're just ignoring the 2's, if I take the x, which is a half, right, and I divide the y, which is square root of 3 over 2, aren't those denominators the same? So I would cancel those denominators and we're left with 1 over square root of 3. Isn't 1 over square root of 3 what our problem is entailing? There it is, right? 1 over square root of 3. So instead of doing all of that, I just tell students, we're going to ignore this because they would cancel out anyway. There's my x, there's my y. So anyway, pi over 3 is the first angle, or 60, but we're going to do it in radians. And then I'm going to slide across, and my other angle is 4 pi over 3. And that makes sense because two negatives dividing by one another causes it to be positive. So that's my other angle. So when you guys are working in your Delta Math platform, you'll type pi over 3, type a comma, and it automatically creates another slot for you, and 4 pi over 3. And by the way, if you just type the letters pi, it will automatically generate that pi symbol for you. So that's it. That's your answer in one revolution from 0 to 2 pi. Let's go on over here. Cotangent squared beta minus 3 equals 0. So instead of using theta, like we did in example 1, we're going to use a beta symbol. That, again, is just a symbol representing the angle measurement. So cotangent squared beta, we're going to take that negative 3 and add it to the 0. So that's just going to be 0 plus 3 on both sides. I need to get rid of the square root, the square, my bad. And so I have to square root both sides. Square root and a square undo each other, leaving us with a cotangent of beta. But when we square root on both sides of an equal sign, we must make sure to include a plus minus symbol on our solution. There's two answers, okay? So we are going to create two branches. One for cotangent beta when it is a positive square root of 3, and one for when cotangent beta is a negative square root of 3, plus minus. Cotangent is still, as in the previous problem, x over y, right? So if I made square root of 3 as a fraction so that it looks like this, square root of 3 over 1, square root of 3 over 1. So here again, instead of like here, 1 over square root of 3, where 1 was our x and y is our square root of 3, it's vice versa. Square root of 3 is the x, y is 1. So positive first. So square root of 3 is x, y is 1. So here is that combination. There's my x, there's my y. So pi over 6 and 7 pi over 6. Make sure you understand that this slide rule, that little technique I showed you there, is only allowed with tangent and cotangent, okay? Only with tangent and cotangent. So this is the answer for positive square root of 3. Now let's do negative square root of 3. So it's either negative square root of 3 and a positive 1 or positive square root of 3 and negative 1. Because this negative, by the way, can go either, that's why I always tell students, put it right here in the middle because that negative can go to either one, okay? So obviously if we just found the first two answers here, that means the other two answers for the negative aspect is going to be over here. So we needed x to be negative square root of 3 and 1, or positive square root of 3 and 1. So both of these, x, y, x is square root of 3, y is 1, x is square root of 3, y is 1. And regardless where you put the negative, the division is still going to end up being negative square root of 3 because we're ignoring the 2's, right? So 5 pi over 6, slide over to 11 pi over 6. So over here, beta can also be 5 pi over 6 and 11 pi over 6. And yes, you can have up to 4 answers. So type these out, put commas, and automatically once you put a comma, it creates a box in Delta Math. All right, let's raise it up a notch in level of difficulty. And notice that sometimes we're going to end up with some squared terms in our problems. And when you see squared terms in our problems, more often than not, you are going to need to factor, okay? So in this case, let us factor using GCF as the first method always to attempt, all right? So notice over here in the previous problem before I start here with this one had a squared factor, but it was easy to isolate it, okay? Because it was just a constant. We plus 3 on this side, and it was easy to square root. But notice the difference with this one. We can't just easily move a number over and solve. It has another sign in it, so that creates a little bit more work for us. So let us take out the GCF, the greatest common factor between these two terms. Well, the 4 and the 2 means that they both are divisible by the number 2, and they both have sine theta in it. So we're going to identify that GCF, which in this case is 2 sine of theta. And remember what GCF is means you're dividing it out. So you are literally, I'm doing this lightly here again, I'm literally dividing every term by the GCF. And the resulting answer of that division, you are going to put it inside the parentheses. So 2 sine theta for this term plus, that reduces to 1. Okay. And now we have a factored format where you guys know what we do is we always apply the zero product property, which says that we take each factor and set up its own equation and set it equal to 0. Okay, so 2 sine theta, set it equal to 0. And then I'm going to do another, I'm going to leave a little space here, 2 sine theta plus 1 and set it equal to 0. And I'm going to solve both of them. So this, I'm going to divide both sides by 2. And so sine theta is just going to be 0. I'm going to subtract 1 and then divide by 2. So sine theta is going to equal -1, divide both sides by 2. So what does sine mean when we are using the unit circle? And hopefully by now you have it memorized from all that unit circle reading you've done in the past. But let's look at our little reference chart here. Sine means that we are looking for the y coordinates on the unit circle. That's what we have to focus on, okay? So I'm going to put a y right here as a reminder. Sine, I'm looking for y values that are equal to 0 and -1/2. So let's pull this unit circle. Let's start out with 0. Y coordinates that are 0. So the only time we see zeros are in these 4 angles, and y is our second coordinate. So that's going to happen here at 0 radians, here at pi radians. So for this one, theta is going to be at 0, at pi, and for this one, where's the y coordinate? -1/2. All right, so this is my y-axis, right? If y is -1/2, this is where my negative values are, right? So that means I'm looking for y's down here. I don't even have to look up here. That's where y is positive, right? Y is only going to be -1/2 here and here, right? We're not going to use this. Those are in the x position, right? So y is here, here. So what are those numbers? 7 pi over 6 and 11 pi over 6. 7 pi over 6 and 11 pi over 6. And so, again, here's a situation where we had two equations that yielded 4 answers. Okay, let's go over next door. Another GCF. Do you notice that? Hopefully you did. So we're going to repeat what we did on this side. I'm going to put a little dividing line here so we don't get them mixed up. Identify the GCF. And we're using the letter X this time for our variable that represents angle of measurement. So if this is my GCF, again, you are dividing, in essence, by that term. So this, if I divided it, will end up as cosecant x. This would end up as a 1. I have two factors that I need to set equal to 0, this one and this one. So I'm going to set cosecant x equal to 0, cosecant x minus 1 equal to 0. So cosecant x is going to equal 1. This one, I don't need to do anything, right? So here's the big takeaway from number 4. Why am I doing this one when it's just like this one with GCF? Well, here's why. Not only practicing GCF is a great thing, all right? So we're going to factor on this one. Get my hand out of the way. Factor by GCF, all right? What I want you to also notice is if you have a reciprocal of identity, all right? If you have the reciprocal cosecant x or the other one, secant x, you know what? I'm going to put theta just so it doesn't have too many letters. Let me put theta. If you have a problem that involves cosecant and secant where you had to solve for them, I want you to revert to the reciprocal it is lined up with. So for instance, cosecant theta is the reciprocal of sine theta, and secant is the reciprocal of cosine theta. And so what I want you to do is that when you get to this final position where you have isolated, I need you to take the reciprocal of that trig function. So cosecant is sine, right? So cosecant, let me rewrite this. We know that cosecant x is equal to 0. Let's write 0 over 1 right now. I'm rewriting 0 as a fraction, okay? Why? Because I'm going to take the reciprocal of cosecant. The reciprocal of cosecant is sine. And so if I take the reciprocal of this side, I have to take the reciprocal of this side. And so I end up with this, okay? Cosecant x equals 1. 1 is the same thing as saying 1 over 1. The reciprocal of cosecant is sine x, and the flip of 1 over 1 is still 1 over 1. So I'm just going to put a 1. Okay? 1 cannot be divided by a 0. That's an undefined value. Okay, so we're undefined here. So there is no solution to look for on this one. All right? Over here, they're asking us for sine 1. Sine means y. So let's look over here. Is there a y coordinate where there is a positive 1? And again, the 0 and 1s are only right here. So that's the only places you should be looking. And actually, there's only one place where y is a positive 1. Don't get pulled in with this one because this one's negative 1. We wanted just a positive 1. Pi over 2 or 90 degrees is the answer. We're working in radians. So we are going to say that the angle x will only have a y value of 1 at pi over 2. So that's my answer. It only has one answer for example number 4. All right, 5. more factoring, but this time we are factoring a trinomial. So factoring a trinomial, let us review how to do that. So if you want to visualize this trinomial like 4m squared minus 6m plus 2 equals 0, you can visualize it like a polynomial, right? Like what we did way back when. So that's all we're doing. The only difference is instead of using variables, single letter variables, we are using a trig function in its place. The rules still apply. What's the number one factoring method we always do? GCF. Identify the GCF as 2. Divide every single thing by 2. We can't use theta because not all of them have a cosine theta on them. All right, there's our trinomial, right? Let's check. This times this is 4, that's 6, and that times that does 2. All right. So we have a trinomial whose a value is a number other than 1. So we are going to have to factor by grouping, right? So first, let's figure out what those middle terms are going to be. Here's this big X organizer that some students use. Use the method you have been practicing with all along. So A times C, we first start with our AC value. So I'm going to put AC right here. A times C, and this is our B value. A times C in our problem is a 2, and our B value is the middle term is a -3. And we need to know what two numbers multiply to be a 2 that at the same time add to be a -3. So I'm going to circle the operations here. All right. Some students do it like this. What times what equals 2? What plus what equals -3? So whichever one is your, hold on, I put AB, I meant AC. Whichever way is your way of organizing your thoughts, just be consistent with it, okay? So let me box this in so it doesn't confuse us. So have you figured out those two numbers? Okay, if you have, did they match the -2 and 1? So -2 and 1 satisfies these two um, questioning techniques that help us rewrite this trinomial in 4 terms. So I'm going to bring back down this 2. This 2 on the outside is just hanging out, by the way. So we are going to replace this middle term with the two numbers we just found. The -3 is going to be replaced with these two numbers. So 2 cosine squared theta, nothing happened with that one. -3, which is this, is going to be changed to this. So -2 cosine theta, -1 cosine theta, and then that +1 comes down, equals 0. Don't worry that I'm writing. We'll see about this somewhere else. And now that we have 4 terms, we can split it right down and factor by grouping. Again, GCF, that infamous GCF, one of the most powerful factoring methods, okay? Hanging out, nothing, that 2's not doing anything. What's the GCF here? The GCF, well, they both have 2's, they both have cosine theta, so I'm going to write 2 cosine theta, open parentheses. If I divide by 2 cosine theta here, I'm left with cosine theta. And if I divide by 2 cosine theta here, I'm going to be left with a 1. They're going to cancel each other. Then I'm going to put a minus. Why a minus? Because I always take the sign of my third term. The next group, whatever that first term sign is, that's what comes down. They both are divisible only by a 1. No other trig function or anything like that. So if I divide this term by -1, it's going to turn to cosine theta. And if I divide this term by -1, it's going to end up with -1. And what I'm hoping to see is that these terms here match. That's what I always hope to see. that the remaining factor after you've pulled out the GCF match, and it did. So my number 2 hanging out comes down. The GCFs go in a parentheses. The of factors that are alike go in a parentheses. And let me set equal to 0. Now I am ready to apply the zero product property. I'm going to set this equal to 0 to solve. And I'm going to set, let's do this. Let me do this one. I'll do the other one below. So I need to add 1, divide by 2. So cosine theta is going to be 1/2. Or let's do this one. So I'll come over here and go like this. We have cosine theta minus 1 equals 0. I need to add 1. All right. What is cosine? Cosine is, check out our chart. Cosine is our x-coordinate. So what am I looking for? I'm looking to find where is x. Let me put an x right here and an x right here, just to remind me, right? Where is x 1/2? Where is x a 1? So where, I'm going to put theta is my where. Which angle is what I'm asking. So theta is going to be the cosine inverse of 1/2. Theta is going to be the cosine inverse of 1. What's theta? So where's 1/2 x? Let's look over here. So 1/2 is going to be x here. Where else? These are negative x's, and right here. Those are my only 2 x values where x is 1/2. So that's what? Pi over 3 and 5 pi over 3. So for this one, it's going to be pi over 3 and 5 pi over 3. Where's x a 1? So where is x a 1? Take a moment. Alrighty, so x is only going to be 1 right here, right? It's negative over here, so it's just this one, so 0 radians. And this is my answer. Okay. One more to go. Number 6. So let's see if I can do this. Alrighty. Let us solve for secant. And then something's happening here. You know what I'm going to ask you to do? Just for the sake of not confusing you, I'm going to make that x a theta when I write it out, okay? Just easier because it's just too many letters. So square root of 2 secant of 8 over 7 theta. Okay. And that negative 2 is going to move over as a positive 2. Then I need to divide by square root of 2 on both sides. So now I have secant of 8 over 7 theta equals 2 over square root of 2. So all along before, after our trig function, we always had a variable, whether it was an x, a theta, a beta, or a theta. Notice every one of these symbols had an invisible 1 in front of the theta, an invisible 1 in front of the beta. There was an invisible 1 in front of the sine theta, invisible 1 in front of the x. And then we come over here and Hanlon goes, oh, let's try a harder one. So in front of the theta, there's no longer a 1, there's a coefficient. I want you to ignore that for now. So actually, literally, just pretend it's not there. We don't care. Do the problem like you've been doing it all along. Secant theta equals 2 over square root of 2. Now the thing is, I told you, if you guys end up with either secant or cosecant, remember up here, I want you to revert to this side, okay? So my secant's going to turn into cosine theta. So I'm going to take this secant and I'm going to turn it into cosine, and I'm going to bring down 8/7 theta. I'm not doing anything with the inside. And since I flipped this one from secant to cosine, I took the reciprocal. I've got to take the reciprocal of this. So square root of 2 over 2. What is cosine? Again, I still show you the chart, but I hope you guys already are telling me you know cosine is x, right? So I am looking on the unit circle where square root of 2 is going to be an x. Where is that going to happen? A positive square root of 2 over 2. So the only time x is going to be a square root of 2 over 2 is right here at pi over 4, positive. That's negative, that's negative. There's my other one. So the only two times x is square root of 2 over 2 are these two angles, pi over 4 and 7 pi over 4, right? See, square root of 2, square root of 2 in the x position. So pi over 4 and 7 pi over 4. So I am going to write, usually what you've been doing is writing theta equals, you see, theta equals x equals. Here, instead of saying theta equals, and let me write down those two numbers again. They were pi over 4 and 7 pi over 4. Pi over 4 and theta equals 7 pi over 4. Actually, for our problem, it wasn't that, right? Like the previous ones, it was that theta. So I need to put the coefficient 8/7. It's not a 1 like the other ones. Okay, but the good news is you guys are very good at solving these with fractions, because last unit, all you did was solve equations like this, and all you did was multiply by the reciprocal. So this went over to this side and multiplied as a 7 over 8. This went over to the other side and you multiplied by the reciprocal. So 7 pi over 4 multiplied by 7 over 8. That's it. So now we just do some arithmetic. Pi times 7 is 7 pi. 4 times 8 is 32. That cannot be reduced. 7 pi times 7 is 49 pi over 4 times 8 is 32. And there you have it. You have solved the equation. So the only difference this problem here has to anything else is that when you get to the last step where you do theta equals, you actually need to write this whole thing. Think of this whole thing as your theta. Write that whole thing equals to the angle you found on the unit circle. So I found pi over 4 and 7 pi over 4, so I took my whole thing, set it to pi over 4, take my whole thing, set it to 7 pi over 4, multiply by the reciprocal, and you are done. And that, my friends, is how you solve trig equations, and using the unit circle as reference to help you solve. Otherwise, you would just cosine inverse with the calculator. And right now, I just want you to make sure you know how to use the unit circle to find those solutions. Time for homework. Thanks again for watching.